So I will like record these sessions, whatever we go over, I'll record it and post it for you on YouTube and link to that on D2L if you can't make it. So there are 4 sessions, but really if you say, you know what, my time is limited, what is the minimum that I should attend? Plan on trying to hit these sessions, 4 to whatever Dan and I were talking earlier about, 4 to 6 maybe max on Wednesdays, where we'll go over the notes, go over homework questions, do some extra examples. So if you can come Wednesdays, then that should be enough. If you are like feeling uncomfortable, or maybe you just have some extra time and you like learning Calc 3 is tough enough, so I want to see some more examples, you can come to the 2 o'clock ones too. But you do not need to come to those. Does that answer your question?
Yes, it does. My other question is, so we're finishing up chapter 15. Do you have estimated date on when we are going to have the exam?
Yeah, I'm gonna have that for you in half an hour when we take a break. So I have, first I had a plan and then I didn't write it down and I didn't want to decide while everyone was waiting for me to decide. So we'll have that before we leave tonight.
Perfect.
Yeah. Cool. All right. Good. Anybody else? I know we had a couple people join a little bit late. You might have missed some earlier announcements. Any other questions about anything?
No.
No? Okay. Feel free. I've got the chat window up, so feel free to post something there, or, you know, the muting and unmuting is totally up to you. Like, I'm comfortable if people leave themselves unmuted and just kind of pop in. If you have background noise, just mute yourself, and, you know, whatever, it's fine. If you have to talk to somebody else, if you want to interrupt me, there is a way to raise your hand. If you click on your screen and click on participants, then there's a way to raise your hand. You can do that there. Or you can just type in the chat, or you can just unmute yourself and just talk. Like, it's totally fine. If you interrupt me, it's fine. I'm not worried about it. Okay, so I think we had a request before for a homework question. So let me pull that up and get the e-textbook up here. Which one were you interested in?
It's section 15.5, number 43.
15.5, 43, okay. And part of me is trying to figure out the new sequence. Like, I'm so used to having everything prepared. If you saw me in my regular daytime class, I got all my material up, like homework's ready and stuff, and now I do not. So I gotta figure out this new rhythm. 15.5, number 43.
Correct.
Okay, so I'm in the textbook. I should have actually, let's go to 15.6 and then work backwards. Because we'll be at the beginning of 15.6.
Page 971.
Oh, awesome. Okay, I'm only 2 pages away. And one more page. Okay. How do I get rid of, here we go. I want to get rid of the contents. How do I get rid of that? Okay, we are consider the following functions. There should be a way to like minimize this thing on the left here. Oh, there we go. There we go. Okay, considering the following function, we want to sketch the XY plane showing the point and the level curve through the point. All right, am I on the right problem? Number 43 here? Okay, excellent. So let me do this. Let me do a little snip of this, and then I'm going to go over to, I found out this way would work pretty well, Rudy, to kind of like snip and then paste, you know?
Oh, you figured it out?
Well, I found a way. I don't know if it's the best way, but there it is.
It works.
It works. Okay, so what's a level curve in general? Like, what is a level curve? How are we going to draw a level curve if, you know, if we don't know what one is? So what's a level curve? Anybody have a good description?
Well, you put C at the where fxy is, and then
correct. Yep. So a level curve is basically when you hold z constant.
Yes.
Right? So we want to find a level curve that would be at the height above the 0.2, -4. Okay? So you have to imagine, I don't know if I can draw this quickly, but you have your XY plane, X, Y, and here's Z, and you have 1, 2, 1, 2, 3, 4. You have this point, and somewhere above or below that is the corresponding Z. So how can I find the Z that corresponds to that 2, -4?
That's where I'm stuck.
Yeah, right, right. It's easier than you think. It's just phrased awkwardly here. It's not an obvious answer, but it is easier than you think. Yeah, Zubair is right. You just plug that in, right? Because the 2, -4 is the domain value. So all we would do is say, well, let's find out what f of 2, -4 is. That's 8 plus 4 times 2 squared plus 2 times -4 squared. 8 plus 16 plus 32, 56. So that's the Z value. That's the Z value when X is 2 and Y is -4. And so what we want to do is we want to then find the level curve through that point. So it means we want to let C be equal to 56.
Okay.
And then you can draw that. Oh shit, I went down too far. Can't see my writing. So 8 plus 4x squared plus 2y squared equals 56, and then just kind of simplify this. 48 divided by 4. I'm going a little quickly here. This might be a bad idea, but I think that looks correct. Might have gone a little faster. It's going to be something similar to that. So what is that, I guess, if you had to draw it? You can just use Desmos or something to graph it, but
Circle? A sphere?
Almost. It's not a circle. Yeah, it's not quite a circle. It's similar. Yeah, it's, well, not ellipsoid. This is just 2 dimensions. So this would just be an ellipse.
Ellipse.
Yeah, just an ellipse. Sorry, did I interrupt you, Rudy?
That's all right. I just kind of jumped in.
Okay. Yeah, so this would be an ellipse. And I can zoom in. Whenever I see people like go like this, I'm like, oh, maybe I should zoom in a little bit, make it a little bit bigger. So that would be, it's kind of an awkward ellipse. It would be x squared plus y squared over square root of 2 squared equals square root of 12 squared. So it's an ellipse. Oh no, we have to divide by 12. We have to get equal to 1. So if we want to graph it, we divide by 12. So x squared over 12 plus y squared over 24 equals 1. And then it's an ellipse where you go out square root of 12 each way in the x direction and square root of 24 each way in the y direction. And then you have an ellipse. Yeah. Let's see what that looks like. Not used to being at home. I don't have things muted here. Holy cow. Okay. I posted a couple of graph tools in, oh, I think I posted them there. I know I have them in my other class. Shoot, did I put them here? Under course information, there's a couple of good online graphers. Yeah, so GeoGebra and CalcPlot3D are both good graphing tools. And let's see what this one looks like. F of x equals 8, what was it, plus 4x squared plus 2y squared? Oh, f of xy, sorry, not f of x. Oh, it's really, there it is. We're just starting to see it, right? It's really high. Oh, this is not great because we, yeah, this is not going to be great. You do see that the cross sections are ellipses, though. I don't know if you can see that.
Yeah.
Right, it's elliptical. We'd have to go really high up, and like my computer is like dragging. Plus, I don't have the right. I don't want to spend time trying to get it, but you can kind of see at least that the cross sections are ellipses, so that makes sense and confirms with it. Yeah, Maddie, somebody's got some paper moving in the background. So, all right. Any other? Are we good on that one, Christian? That was
Yeah,
the
yeah,
one
we're
you
good.
asked about?
Thank you.
Okay, excellent. Good question. That was a good one. Any other? Let's do maybe some homework questions still. Does anyone else have additional homework questions that you wanted to ask? So the best way for us to use this time, and you are trying to get a whole new rhythm, and I totally understand that, but let me do this. Let me do a little poll. Okay, I'm going to do a poll. And I want you to be honest. I think I have to do it on this page. Okay. Which videos have you watched? Okay, so oops. And we'll do anonymous. I'm just kind of curious. See if this works here. Save. Okay. Oh, it didn't work. It worked earlier. I did a poll earlier. Oh well, good thought. So the question I was going to ask is I'm just not sure what sections you watched. So the ideally you've watched all of the videos from 15, 5, 6, and 7, and there's going to be stuff that you're like, okay, I did not follow that. That's just how it works. Like I always get interrupted in class. So it's not possible for you to watch 3, like an hour and 40 minutes of videos and not have any questions whatsoever. So the best thing to do here is come and say, could we go over this example? Could we go over this page? Could we do that? So I'm just going to do a quick overview of the different sections, and you can stop me at any point if you have some questions. Okay?
Good.
All right. I'm going to mute Christian. Sorry, because Maddie was commenting. We could hear your paper rustling. So no big deal. So in 15.5, there's 2 main topics. It's directional derivatives and gradients. Directional derivative is basically the slope in a specific direction. And then the gradient is telling you, it's super helpful. It's got a variety of cool things, but the gradient is really telling you which direction is steepest. So the directional derivative is giving you a slope. The gradient is giving you a direction. The directional derivative gets you the slope in whatever direction you want. And we had some derivation of that, and you end up with this end result here for the directional derivative. It's the partial derivative with respect to x times cosine of whatever the directional angle is, plus the partial derivative with respect to y times sine of whatever the angle is. And that you'll see that is not a vector. That's just a number. That's just a scalar. So directional derivative is just a slope in a specific direction. And then the gradient, what the gradient is the gradient is a vector. It's just the partial derivative with respect to x, that's the x component, and then the partial derivative with respect to y, that's the y component. And the gradient gives you the steepest direction, whatever direction is steepest. And then the opposite of the gradient then would be whatever is steepest in the negative direction. And then orthogonal to those two would be the direction of no change. A couple of key facts about the gradient. If you get the gradient of is the zero vector, that means the steepest direction is staying right where you are, which means you're right at a peak. If the gradient is 0, you're right at a peak. And that's this statement right here. So if the gradient is 0, then the directional derivative is 0 and you're right at a peak. So we proved those. Then we had this key result that, and we did a little investigation there, but we had this key result that the gradient is always orthogonal to those level curves. So for example, let's look at that homework question. Where did that go? Oh wait, actually I want to be right where I was. just different tab. We had that homework question. So let's look at a specific point on that level curve. So we have that level curve, we had the point 2, -4, 56, okay? So let's find the slope of this level curve at the point 2, -4. So this is a Calc 1 problem. They would take the derivative with respect to x of both sides. Actually had a question like this on the test they had yesterday. Just implicit differentiation, take the derivative with respect to x of both sides. So we get 2x plus y dy dx equals 0. And then dy dx will be -2x over y. That's the slope of that level curve at any particular point. So the slope of the level curve at the point 2, -4 will be -2 times 2 over -4. Oh, that was unexpected. The slope is 1 there. Okay. So that's the slope of the level curve. Now, I did not prepare this example ahead of time, but if our theory is true, the gradient vector at that point should be orthogonal to that curve. Okay, so let's see what happens. So the gradient vector of our function f, it's the partial derivative with respect to x, and then the partial derivative with respect to y. Go back up here a little bit. Here's our function, 8 plus 4x squared plus 2y squared. So what would be the partial derivative with respect to x for that function?
Would it be 8x, right?
Yes. It sounded like you were going to say more. I'm like, don't say anything more.
No.
It's just 8x. Yep, Zubair had it right too, 8x. And so similarly for the partial derivative with respect to y would be 4y, right?
Y, yeah.
Yep, okay. So let's find the gradient at this point. At 2, -4. That's, let's see, 8 times 2, and then 4 times -4. So that's the vector 16, -16, okay? So here's what we're saying. If we look at that level curve, now it's up at a height of 56, but if we just draw it in the xy plane, it's an ellipse, it's a little taller in the y direction, something like that, and there's this point down here that's 2, -4. That's that level. This is the level curve, x squared plus y squared over 2 equals 12. I was telling my other class, I've used a tablet like this before, but not this much. So I just started using it this often. And like I'm like in love with this pen, and I don't know if I can go back to writing on paper, because all I have to do as I'm writing is just click, and then it's an eraser, and then I unclick, and then I can keep writing, and I can change colors. It's like the coolest thing. It's like the coolest thing. I think I'm gonna go up to, yeah, I think I'm gonna go back to it, like keep it when I go back to the classroom. Oh, speaking of, anybody thinking of summer classes? I don't know if you are. Expect the schedule to change.
Are they going to online?
I'm not certain. I know there are discussions of that. Yeah, there are definitely discussions of that. So just be aware, keep your, keep looking for emails about summer and just keep your head out. I know, because the governor extended like my kids are out for another month.
Yeah, till April 30th.
Right, at least, who knows, and the ECC is like, they do not want cases to pop up at the campus. So Maddie, you had your hand raised too. Did you still have a question?
I'm normally a Wabansi student, and they already got about 4 over here. Yeah, that's the known ones at Wabansie College. They don't even
Yep.
want to open the campus at all.
Right. So yeah, Maddie, I got it. So yeah, so just keep an eye out for that. I know they're in discussions about summer, and it's totally up in the air. And there's discussions like, because right now it's like we're just trying to make it through. We have all these classes like this that are like not great online. Like no one would really choose to do this, right? We don't have an option, so we're making the best of it. So, and this virus is not just going to be gone. It's going to be around. It's probably just going to be like the flu. That's kind of what they think. Like it's just going to be cyclical. And so we have to like, now it's totally new. That's why it's called a novel coronavirus. It's new. And so no one has any immunity to it. And so the question is, what level of risk is acceptable?
Mm-hmm.
That's where they are right now. And like, you know, no one has a great answer for that because they don't really know what the risk level is. So that's why people are like, slow down, slow down, slow down, slow down. Let's just, you know, so like summer, they might just say, let's keep it to summer. Let's only do classes that have been online before. You know, that might be an option that they might do. Yeah, I don't know, which sucks because then a lot of students are like, well, that sets me back a semester, you know? So yeah, I would imagine for the ECC community, has to be cases in the student body. There's just between the faculty and staff and students, there's 10,000 people.
Right.
Like, I don't know. It's a lot of people that have no cases. So, but we might not know about it. I don't know. So I just thought about that when I don't know, I got distracted there somehow. So I'm easily distracted. You will find that. Sorry about that. So
You ain't the only one.
so we found that the slope of this line here was 1. Right, that was the slope of the tangent line. That was the derivative. That was the Calc 1 problem. My Calc 1 students could have done that. We found the slope of that tangent line was 1. We found our gradient was the vector 16, negative 16. Well, if you draw that from this point, 16, negative 16, if you had to describe the slope of that vector, what would you describe as the slope of the vector? What do you think? Goes right 1, or right 16 and down 16.
It also equals 1. No?
It went down 16 though.
Oh, negative 1.
Negative 1. Yeah. So this is how good I am, just like proof of competence here. We just totally made up this example to like use the previous homework question to prove, or maybe not proof, no, it's not a proof. To demonstrate, here's an example where the gradient vector was perpendicular to the level curve. And that's a fact about the gradient vector, that it's orthogonal to the level curves. So if you pick a point, you find the slope of the tangent line at that point on the level curve, the gradient will be orthogonal to that. So that's one of the facts about the gradient. So that was kind of a spur of the moment example. Any questions about that example? I did a lot of stuff really quickly that I'm comfortable with, but you know, you just watched a video maybe. So any questions about how I found the gradient? Anything there? Zubair, the slope of which? The slope of the original, the level curve, or the slope of the gradient vector? So the gradient, we're kind of looking at the slope casually here. We could have done this a variety of ways to prove that they were orthogonal. But you can just think, well, the slope of this line is it went down 16 and then to the right 16. So kind of thinking of a slope like that. We could also have taken this line and written it as a vector. I don't know if that sounds familiar, where you have that vector, let's see, it would be 2, negative 4, plus t, and then a directional vector, it just goes up 1, right 1. So 1, 1. That could be that line in parametric form. And so you have this direction vector, that's the direction for the line. And then you have your gradient vector. And how can you prove that those vectors are perpendicular? Do you remember from, was it chapter 13, all the vector stuff? How do you prove, yeah, dot product is 0. Yeah, dot product is 0. So if you take their dot product, 16, negative 16, dot product with 1, 1, you get 16 minus 16 equals 0. There's another way to show that they're orthogonal. Yeah, that's all good in here. It's all good. Okay, so let me go back. That was one question. Zubair, did that answer your question? I think so. Good. All right, that was it. Any other questions on this example? How we did a quick example of finding the gradient, and then we also kind of used it to show that the gradient was orthogonal to the level curve. Any other questions on that one? Okay. So let me pop back in here. So that was that last fact from 15.5. 15.6, it's interesting. This has been a fascinating semester for a variety of reasons, but for one good reason, I've been teaching Calc 1 and Calc 3 at the same time, and we're like moving in parallel tracks. We're like doing all the same things, but you're doing it in 3 dimensions. So they learn how to find slopes and find equations for tangent lines. You learn how to find vectors and equations for tangent planes. So that's what this section is about, how to find an equation for a tangent plane. If you need an equation of a plane, how do you get an equation for a plane? What do you need? That's like a chapter 14, right?
A vector and a normal vector, I think.
Normal vector,
And
correct.
then a point.
Yep. And a point, correct. Yep, you need a vector that's orthogonal and a point. Yep, very good. So the beginning of that video, 15.6, kind of derives how to get that normal vector. And the normal vector that you use is actually the partial derivative with respect to f, with respect to x, the partial derivative with respect to y, and then -1. Why is it -1? That's what the video is about. So the proof here is about why it's always -1 for the normal vector. So if you want, you can think of this formula. Here's a formula. You can also just think, well, I'm just going to use the regular old plane equation. Right? There's your regular old plane equation. And the normal vector is the partial derivative with respect to x, partial derivative with respect to y, -1. And that's what's in the box here. It's just kind of written out like a formula. And that's how you can get a tangent plane. So you have those 2 partial derivatives, and then the z is always -1. And again, the reasoning is in the video for that. So there's, then the second one here is if it's implicitly defined, it's very similar. The c is then the normal derivative with respect to, or it's the partial derivative with respect to z for that, that normal vector.
What does it mean when it says it's implicitly defined?
I
Yeah,
was just
so
about to ask that.
good question. Good question. If you think about, I keep going back to, this is like a great homework question, Christian, because it keeps getting us good examples. So if you think about this equation right here from a Calc 1 perspective, they're used to y is a function of x. That's what they're used to. Y is a function of x. That's an explicit formula. Y is explicitly defined in terms of x. If we go down to the ellipse is not a function. Remember the vertical line test? Not a function. So you can't write y as a function of x, but it's still a curve, it's still a path, it's still an equation. So it's called an implicit relationship.
Okay.
Yep. And so ours is the 3-dimensional extension of that. If you can have z as a function of x and y, what you have is some function above the plane.
Mm-hmm.
If you have like an ellipsoid, it wouldn't pass the vertical line test. you have to give those kind of surfaces, you have to define them implicitly where you have the x, y, and z all together. And there's no z equals. So for us, where did we go? So explicit for us means, I almost said y, but we have z. Z is a function of x and y. And then for implicit, it means there's some function of x, y, and z all equal to 0.
Okay.
Yep. So that would be finding the tangent plane to a sphere, right? You could do a hemisphere and solve for z and get z equals, but you can't do the whole sphere. So if you have the whole sphere, you have to do it a different way. Yep, good question. The part here at the end is a little, you don't use this as much. Essentially, linear approximation is essentially saying, if we were to zoom in, oh, this may be a bad idea, but if we zoom in near a point, I can't really zoom in anymore. Oh, that's not as good. On the document cameras, you can like zoom in until you see the ink. So unfortunately, I can't zoom in anymore here, but if you zoom in close to a point, if this gray is a tangent plane, the gray is pretty close to the red, close to that, when you're near that point. But the further away you get, then that approximation gets worse and worse. So it's essentially using the tangent plane to approximate the function. Like, let me see if I can do that. See if we can get a better. I'm going to see if I can get. Oh, shoot. So I have a question for you. Between all of your classes, how many different new technologies have you had to learn?
My only class, so.
Oh, okay. Not too bad then.
I also had to learn Google Hangout.
Google Hangouts, sure.
This is the only one like virtual classroom I have. The other one is just like I think he's just posting videos online for us to look at, and then the homework is online. So that's about it.
Yeah, yeah. I feel like this is having a hard time processing. There's a delay. So what I have here is one of the examples from the notes, and here's this sphere. I don't know if you all can see that. I'm kind of rotating it back and forth, and there's a plane there. And if we zoom in, right near, whoa, there's like a big delay here. I can't tell if the delay is because of my computer or if it's processing it. Now I'm not going to be able to show it, but the idea is if you're zooming right near that point, the plane is almost the same as the surface. The plane is a very good approximation for the surface. So that's what the rest of these notes are essentially about, is saying that you can use that plane. You can use that plane to approximate the surface. And then the last section, this is the most fun. And this is also a Calc 1 thing. I don't know if you remember. Do you remember doing like find the largest box? And
Yeah, but this one's hard.
Optimization.
No, I mean, all the fun stuff is hard, Christian. I mean, come on.
I had no problems with the previous two until I got to this one.
You're like, what is happening? So the idea here is it's basically like Calc 1 where you have a function. You might have to make it yourself, and you want to maximize it. You want to find out when is it the biggest possible, or minimize it like smallest cost or something like that. And so you have to find these peaks. You have to find these peaks or a minimum little valley. And so if you recall, the gradient, where did it go? The gradient is 0 at those points, right? I can't find it now quickly. So if the gradient is 0, then the directional derivative is 0. So that when the directional derivative is 0 in all directions, you're at either a peak or you're down at the bottom in a valley. So what you have to do is find the gradient and set it equal to 0. So you set the partial derivative with respect to x equal to 0 and the partial derivative with respect to y equal to 0. That's how you find those maximums and minimums. So that's this relative extrema in 3 dimensions. It means the partial derivative with respect to x and the partial derivative with respect to y are both 0. Yeah, they're both 0. Do we have someone, Devakar? That sounds like a student. I'm going to let them in.
Okay, so I had a question on this section actually.
Yeah, go ahead.
So on 15.7, example 7, during the notes you had h equals 0 and w equals 0 for like the one of the, what do you call it, equations.
Like, yeah.
And that's when the audio cut out when you explained why you cross those out. So what was the explanation for that?
Yeah. So if you think about this, we're trying to find the largest box. And so we're trying to find the maximum volume. So think of say you can shape cardboard however you want, and you want to make a cardboard box. If your box has height 0,
right,
what's going to be true about the box?
It's not a box.
It's a piece of cardboard.
Right.
But that's like a critical point, but it just happens to be a minimum, not a
Gotcha.
maximum. So just using logic, like, well, if the height is 0,
Right.
that's not a box. So I'm just going to cross that one off. It is a critical number. It's a valid critical number. And so there's a point that associates with that. If the height is 0, then all of the, like you just have one big sheet that's all width and length. That's relevant. That is a critical point, but it just has a volume of 0, so it's not relevant for our particular example.
Gotcha.
So usually you end up ignoring the zeros because you're interested in maximums, not minimums, usually. Not always.
Right.
Not always, but usually.
Okay.
Yeah. So same thing for the height, or for the height, and for the other one was the width. And so yeah, we skipped those. They're relevant, but I'm not going to finish solving those because they're just going to give me a volume of 0.
Okay.
Yeah, good question. There are like 2 challenges that usually occur on these. Maddie, I'll get to your question later. I'm going to take a break in a couple minutes here. The 2 challenges in these are, number 1, you have to make the function that you want to optimize. So that's usually the first challenge. That's not always given to you. Often you have to construct that. There's enough information to you, like here, this one, number 6, find the maximum volume. Well, volume is length times width times height, but that's a function of 3 variables. So somehow I need to get it to be a function of 2 variables. Well, I have this constraint that the x, y, and z have to be on the plane. So if I can use the fact that they have to be on the plane, then I can get an equation, a function that's just a function of 2 variables. So to use this method, you have to get a function that's a function of 2 variables only. And that's all algebra. That is not calculus. There's no derivatives there. There's no limits. It's just algebra. It's multivariable algebra, so it's not trivial algebra, but it's all about constructing that function. Most people are pretty good at taking partial derivatives. So you take some partial derivatives with respect to y, with respect to z or x or y or whatever your problem is. Most people are pretty good at that. But then you have this algebraic system of equations that you have to solve. And sometimes those are easy. There's ones we did earlier in the video that were like almost trivial. They were so easy. This one was not. I think the next one is also not trivial at all. There's some homework ones that are not trivial. And so solving that algebra can be a challenge. You might use some graphing tools if you want to help you kind of wrap your head around what's working. They usually involve some kind of either addition method or elimination method and then solving it from there. Incidentally, you'll notice the 2 hardest parts: algebra, making the function, and algebra, solving the system. Those usually tend to be the limiting factors on these optimization sections. So the key is, watch the video. Maybe we can do another example. I can pull one up from the homework. And like the more examples you do, you start to like notice trends for strategies that occur frequently. And that's really going to be the key. All right, I'm going to take a little break here. And I think what I'd like to do when we come back is actually try an optimization problem. I'm going to stop my screen share here. Now let's take a 5-minute break, maybe come back at 5:05, and we'll talk about the plan for the quiz and exam, kind of answer some questions about that, about what to do next. And then we'll do an example, at least one example of an optimization problem. Yeah. Cool?
All right. Sounds
All
good.
right. Yeah, 5 minutes. So we'll be back at 5:05.
Okay.
All right. Kind of trying to find a good example here. Oh, so I think for the quiz exam answer, I don't know if this is the right solution, but I don't think it's great to, after 2 weeks off, to come back and have an exam, and also with a new instructor, like have a new exam that first week. It seems like a bad idea. So I think what I would like to do is give you a quiz, and I don't have it ready yet, but I'll post a quiz over these 3 sections, 15.5 to 15.7. And since we're not in a great rush here, why don't I promise to get that posted by 8 a.m. Thursday, so tomorrow. And then you can take, my point is that it's a quiz, not an exam, so it should be like a half hour, so make sure you got yourself some time. And then just submit it by the end of the day. I'll have a Dropbox for that, 11:59 p.m. And I appreciate everyone who took the time to submit some practice PDFs. That was really helpful to kind of at least give you some time to try that process. So if you haven't yet, if you need help doing a PDF, I've had good luck with Adobe Scan, but I have an Android. My wife has an iPhone, and the Notes app is really good. You can make PDFs pretty easily using the Notes app. So what I'll do is I'll just post the questions. You don't have to have a printer. You just use your own paper. I'll just post the questions. You just handwrite your work, take a picture, make a PDF, and then upload to the Dropbox that I'll put out for that. Okay. Did that answer your question, Zubair? Yeah, I think that's a good solution, to use Notes. That, you know, it's hard because I don't have every device and everybody has their, the thing is you want to find something that can make a PDF, because that's really easiest for me. It's easy for me to import it. And I know that we practiced it last night on my wife's phone and we were able to do it. I can post some directions. I think I've posted them already, but I can post them again. I don't think I've posted them for Notes. I think I have for other classes. So I can post those directions. Yeah, Adobe Scan does seem to work really well. It's free. I think you have to make an account, but whoops, sorry. But it seems to work really well. And then you can even adjust the contrast and everything after to make it legible. So yeah, I think that'll be the plan. And then for the exam, I really think you're going to need feedback from the quiz first. And so I think we're going to do, we've done this in my other class as well, where there's a little bit of a lag. So like we finish the material, we want to have some time to reflect and ask questions, and then we have the exam after that. So I think a week from today, we will move on. We'll talk about 15.8, the next section. We'll talk about beginning of chapter 16. And then we'll have the exam kind of from the previous stuff posted and available after that. So the exam will not be until after we meet again. So the reason is,
Would be Friday.
probably just post it on Thursday again.
Oh, Thursday, and then do when?
Do Thursday night. You have a day to work on it. If
Oh,
you have
yeah, I'm sorry. I'm thinking today's Thursday, so.
Yeah. So
Okay.
So we'll do the same thing next week, where
Yes.
we'll have a class. We'll answer any questions. This time you'll have time to get feedback from your quiz. I can't promise moving forward, but that'll give me some time to, and for you some time to get caught up, and you have a lot more work. You know, I think if we were on a regular schedule, today would have been a good day to post the exam and have you turn it in tomorrow. But we are nothing is regular about your class. So and it's not your fault at all. So I think that seems good to post a quiz for you to work on 15.5, 6, and 7. I'll post that by 8 a.m. tomorrow. You can have all day to work on it, submit to D2L. I'll try to get that graded and back to you. And then we'll have more videos to watch. Next week, we can answer questions on the quiz. We'll move on to 15.8, probably 16.1, maybe even 16.2. I'll see how long those videos are. I don't want to like give you like 2 hours worth of videos. That's too much. But you know, have a couple sections to do the same kind of thing. Talk about the notes, answer homework questions, maybe do a couple extra examples.
How hard is the next chapter? It's double integrals, triple integrals, right? Is it harder than
How
this
are
one?
your integration techniques?
Not bad.
Yeah, then it's fine. Yeah.
I just gotta review
And we don't do
couple
like, yeah, we don't do some of the crazy
trick
techniques.
sum is easy. I mean, yeah.
That one, yeah. So I would say that I think the last chapter is our hardest.
Yeah, it combines everything, right?
Correct. It's very cumulative. The integrals, I think, are really just an extension of Calc 2. Like, I feel like the partial derivatives we do now, I don't know, those, I don't know, it's not fair to say, but those to me, a lot of that seems very logical and is a nice extension of Calc 1, you know, tangent planes and stuff like that. Like, it seems like it's reasonable. So 16, I think, will be similar, where it's like, oh, this is just an extension of integrals in Calc 1. And instead of finding areas under curves, well, now we're in 3 dimensions. So we're not finding areas, we're finding volumes.
Volumes, yeah.
You know, and so logic, whenever it's logically like, oh, I understand what I'm doing, that helps. You know, so I think in chapter 16 we'll understand what we're doing. Yeah.
All right.
Yep. So everybody got that? If you missed it earlier, we'll post a quiz by 8 a.m. tomorrow. That'll be due to a Dropbox in D2L by tomorrow night in PDF form. If you use multiple pages, please combine them. Just like if you use the Adobe Scan, you can just make you can combine a bunch of images into a single PDF. That would be preferable. So Zubair is saying he used calculators to approximate integrals. It depends on the setting. Like sometimes that'll be okay, sometimes it won't. So we'll talk about that when we get there. We'll worry about that. We'll cross that bridge when we get there. Yeah. Yeah. So it depends on the question. Yeah. And then we'll have the exam. We'll have another class next Wednesday, and then we'll have the exam will be released after that class. So there's a little bit of lag where we're kind of working on new stuff, but you have to be able to ask questions on, okay, I had this quiz, I got my feedback from the quiz. Now I have questions about the quiz. You know, this is really the first time we've met. I like people to have time to have things to simmer and work on homework. And ideally, if we had been on a regular schedule, you would have done that by now, but there's a pandemic, global pandemic, and you just got a new instructor and all this stuff. It's crazy. So we'll delay things a little bit. The downside is we're going to start new stuff. And, you know, you're going to be like juggling in addition to all the other juggling you're doing.
So it seems that we're going to be with you towards the end till the end of the year, right?
Nope, it's been officially changed. There's no changing back.
Okay.
I have another question.
No take backs. You're mine now.
Just to clarify for the exam, so you'll post it on Wednesday after we have our class?
We could do that. I was thinking of Thursday morning again.
Oh, gotcha. Okay.
Yeah, I want to make sure you have all day.
Yes.
Because people's work schedules have changed and they have family, and like one of my students in my other class like put a comment like, I'm sorry, I spent like an hour and 20 minutes on this, but it was interrupted because my daughter, and I'm like,
yeah.
I do not care. I do not care about when you work on it, if you break it up. We're just going to try to be as honest as we can, and I'm not going to be there monitoring you with videos that you're using the formula sheet that you made. You've got a calculator, and then I'm going to supply you with a couple of online tools that you can use during the test, and I'm assuming that that's all you're using. So,
okay.
Yeah.
Thank you.
Cool. We'll talk more about the exam next time too, about what will be on it. If you look, am I sharing or I'm not sharing? So let me share my screen again. I have an example picked out that I was going to try here, so I've got that up. In D2L, under this unit, as you're prepping for the exam, there is, in addition to all the videos and some homework keys, there's a chapter 15 review problems. And so this is actually from your textbook, but I've kind of trimmed it a little bit. You know, the one in the textbook has like 80 questions. It's like, well, I can't do all 80, so how do I choose which ones to do? So I trimmed it to a slightly more manageable 52. So, but these are questions that I think are reasonable and things you should know. And I don't have a key for that, but we can talk about these on next Wednesday. So we can go over some of these examples and, you know, in addition to some of the newer stuff. So that's under the content tab in the end of this unit. So I did find some additional examples here. Where did they go? Here we go. So I thought, let's do a couple. Let's do one that's just kind of algebraic. Yeah, that's correct, Zubair. Lagrange multipliers will not be on the test. We'll go through 15.7. I thought, let's do a boring one. Let's just do like a function and try to find critical points and try to understand what's happening at those critical points. And then we have a more interesting one on the next page. So let me do, which one did I graph? I think I graphed number 29.
33, by the way, is terrible.
33, you tried that one? Not good?
Yeah, that's a lot. That's a lot.
All right, let's see if I can shrink this down. It pastes in really big. So let's try here. Number 29. We're going to try to find the critical points and then use the second derivative test, which hopefully you've taken the notes and you have that test. There are some criteria whether to determine whether it's a maximum or minimum, or the test can be indeterminate and not answer you. So let's do that. First of all, remember to find those peaks. It means the directional derivative is 0 in every direction. And we have the theorem that we said that means the gradient is 0. So what we're going to do is we're going to find the gradient of that function f, and we're going to set it equal to the 0 vector. Okay. So the gradient will be the derivative with respect to x is just 4x cubed, and the derivative with respect to y, 12y cubed. And I apologize, this is a really easy example, but sometimes it's good to have an easy one to start out with. So that's our gradient. That's just the partial derivative with respect to x, and then the partial derivative with respect to y. We're going to set this equal to the 0 vector. That's going to be those peaks or valleys. And so what this means is 4x cubed is equal to 0, and it's important, and 12y cubed is equal to 0. Maybe we should have done a different example because this one's pretty trivial. You know clearly then x must be 0 and y must be 0. So the critical point is the point 0, 0. What you don't know just from looking at it though is that a peak or is that a valley? So you could graph it. I have it graphed actually, but that's not fair. We'll do that just to follow up our work. So there's the second derivative test here. Second partials test. So it's a little, because you're in 3 dimensions, it's not just as easy as finding a concavity. You know, when you do that in Calc 2 or Calc 1, you just find the concavity. If it's concave down, it's a max. If it's concave up, it's a min. So there's a little more to it, but it's similar. So this is what we're going to do. We're going to calculate this D quantity here and then use that to determine whether it's a relative max or relative min. So we need second derivatives with respect to x, second derivatives with respect to y, and then a mixed partial. Okay, so second derivative with respect to x, that's going to be the derivative with respect to x of that first component of the gradients. That's 12x squared. Uh-oh. This is a really bad example. Second derivative with respect to y, 336y squared, and then the mixed partial derivative
0.
is 0, right? The derivative of the 4x cubed with respect to y will be 0, or the derivative of 12y cubed with respect to x will be 0. Does anyone know why this is a really bad example to illustrate the second partials test? The downside of not being prepared. We can keep going. You'll see it when we keep going.
You have to just subtract it from at the partials. You have to square it and then subtract it.
It's worse than that.
Is it inconclusive because it equals 0?
That's correct, Carmela. So we need to evaluate all these derivatives at our critical point, at our 0, 0. And so the second derivative with respect to x is 0. The second derivative with respect to y, also 0. The mixed partial is already 0. And so our d, which is the second derivative with respect to x, multiplied by the second derivative with respect to y, minus the mixed squared, is all 0. So the test is inconclusive. So then we are kind of actually stuck and have to look at the graph. But luckily, I have the graph. Where did it go? It's behind my Zoom window, I think. There it is. Ta-da! Oh, that is really dark on that screen. That is not great. There we go. There's a better angle. Maple is much better than that grapher. The problem with the online graphers is they're processing on the server, and so things can take a lot longer. So here's this Maple one here. Now, interestingly, it looks like, do we need to zoom in? It looks like a minimum there, doesn't it?
Yeah.
But I worry like it doesn't pop back up again, does it? I don't think so. Oops, wrong one.
Almost looks kind of flat.
Yeah, it's pretty flat down there. Pretty clear minimum. I don't know if you remember graphing 4th degree polynomials or 6th degree, like the higher it is, the flatter it gets near the origin. So that's really what this is. This is just a multivariable one. So the test was inconclusive. That sucked. That was a bad idea. But we can see that it is indeed a minimum. So let's do an example that's a little more interesting now, where we have to make our own function. And I think these are the ones that Christian was talking about that are more challenging, where we're trying to optimize something. So let's see if I can get back into the textbook. There are lots of box problems, and I found one that looked interesting.
I have a quick question about that
Yeah, go
problem
ahead.
I just did.
Uh-huh.
So on a test or on a quiz or something, if it's will we have a problem like that if it's inconclusive?
Probably not, right.
Okay.
If I'm asking you to use the second partials test, it's kind of like, well, why did you ask me to use the second partials test? Because I couldn't use it, you know?
Okay.
Yeah.
Okay.
All right. So let's see here. Where was this one? 63 looked kind of fun. Famous last words, I don't know. Okay. So let's try and give this one a go. Rectangular box, volume is fixed at 10 cubic meters. So whatever it is, it has to hold, wow, that is, what is this box made of? 10 cubic meters. This is not a cardboard box. This is a really, really big box. 10 cubic meters. Okay, 2 different materials. The materials for the top and the bottom cost $10 per square meter, and the materials for the sides cost $1 per square meter. We want to find the dimensions that minimize the cost. So we're going to need to try to find a cost function. Okay, what do you need? cost function. That's going to be our function. We call this the objective function. So I'm thinking it's rectangular. So the top and the bottom have the same dimensions. So it would be 2 times $10 times the area of, we'll just say the top, whatever. They're the same. Plus, I need some dimensions, length, width, height. We can't say 4 because we don't know if it's a square. So we'll have to say 2 times $1. All right, Kenny, you're muted. I don't know. Do we have a Kenny in our class? I don't know. I haven't looked at my class list. So I'm like,
I'm here. Sorry, I just disconnected, so I had to reconnect.
we cannot hear you. Feel free to type in the chat if you have a question, okay? All right, so $2 times $1 times, we'll call it length times height for the front and back sides here. And then plus 2 times $1, $1 times the width times height.
Why'd you make it $1?
Isn't it $1 per square meter for the sides?
Yeah, I see it. Thank you.
Yep. So the top and bottom are more expensive than the sides. Okay, so it looks like we have 20 times, what will that be? Length times width plus 2 times length times height plus 2 times width times height. And that's our cost function. There is a problem with that function. We're not going to be able to optimize it the way that it is currently structured. Does anyone know what the problem is?
There's 3 variables.
Correct. And what's usually the case here is then you're provided this other fact that the volume, which of course would be length times width times height, has to equal 10 cubic meters. And that's called the constraint function. That's a constraint. Like you want to build the cheapest box? Well, let me build a tiny little box. Well, no, I have this constraint that the volume has to be 10 cubic meters. You can't really optimize something unless you have constraints involved with the optimization. Like, what's the largest box you can build? Well, I mean, can I spend as much money as I want? Then okay, then I'll just physically the limits of the material. So here, you want to find the cheapest box, but you still have to hold 10 cubic meters. And you can see here, we can just pick one of the variables to solve for. They're all pretty similar, so I don't know that it really matters. I'm just going to solve for L and say it's 10 over WH. You could pick any one of the 3. You'll end up with a function of the other 2, and it doesn't really matter. But now I have a cost function that's only going to have W's and H's in it. L is 10 over WH times W. And there's another L, 10 over WH times H, and then 2WH. So it looks like we get 300 over H plus 20 over W plus 2WH. Interrupt me, stop me if you have a question, just unmute yourself and pop in or raise your hand through the app if you want to. I did not prepare this example, but I'm pretty confident that we're on the right track. Any questions so far? Okay. By the way, you're not used to me, so when I ask if there are any questions, I always wait and give people lots of time. So you might be like, what's happening? wait, is something happening? But I always have this like little counter in my head. So I always, it's not that I'm doing it. I'm like even more now because somebody might be typing something. So I always like when I ask if there are questions, I like put a long delay in there intentionally. So here, remember how we talked about these, that there were two key challenges. And one of the big challenges was making the function. So we're done with that. Here we have our function, but this was all algebra. There was no calculus here. Little geometry basically, but mostly algebra. So now what we're going to do is we're going to take the partial derivatives. Why don't you try that? Why don't you try taking the partial derivatives? We're going to take the partial derivative with respect to W and then the partial derivative with respect to H. So I'm going to give you a couple minutes.
Sorry, I might have done it wrong, but it's the first. Is the 300 over h supposed to be 200 over h?
200 over H. See, this is why. 200. I mean, clearly 20 times 10 is 300, right? Everybody knows that. Come on, come on. All right. Anyone want to share what they got for the partial derivative with respect to W? Oh, Zohab's already on top of that. Look at that. Jeez.
Negative 20 over W squared plus 2h.
Yep. And then Zohab's got the other one. And they're very similar because they're the same structure, just a different constant. So negative 200 over H squared plus 2W. Okay. So again, we have the maximums when, or minimums, when our two partial derivatives are both equal to 0. So what we need is this equal to 0, and we need the second one equal to 0. And what we have then is we have a system of two equations and two unknowns. And that's what these boil down to. We've done actually the calculus in this problem, we just did it, and then we're done. There's no more calculus. The rest of it's algebra. So we did a bunch of algebra to get the equation. We did two like easy partial derivatives, and then the rest of it's algebra. So I always tell my calculus classes that there are two reasons why people will succeed that are kind of like the barometers for success in a calculus class. And one of them is any class. You got to do the work and attend and work hard, you know, the effort and pay attention and all that. But the second is algebra. There's just so much algebra in calculus. It's just brutal if you struggle with algebra. So I think what I would do, I'm not a big fan of the fractions, so I'd probably just clear the fractions. You can do this different ways. There's no right way to do it, no wrong way. Well, no, there's no best way to do it. Let me rephrase it that way. There are some wrong ways, but there's no best way to do it. So if we multiply by W squared, we get negative 20 plus 2HW squared equals 0. And then if we multiply by H squared, we get negative 200 plus 2WH squared equals 0. That was not particularly helpful. I think it was actually, but. Seriously love the pen. Okay. Okay, I need some algebra. We need some algebra. Those are weird equations. I have an idea. Do you? Do you have any ideas?
Could you solve for one of the variables on one of the equations?
Yeah, you could do that. Did you have one in mind? This is Dan, right? Yeah.
Yeah. I don't know. H.
Which equation?
On the first one.
Yeah, you
Oh, no.
definitely want to solve for the one that isn't squared, right? Because you don't
Yeah.
want to have a plus or minus square root. Yep. So that's fine. We could divide by 2, I guess, in each of these. Let's do that. Make it a little simpler. Okay, that looks better. So let's take the first one, solve for h. hw squared equals 10. So h is 10 over w squared. Oh, and then we could substitute into the other one, right? So negative 100 plus w. Whoa, this is going to have some weird answers. W times 10 over w squared squared equals 0. That's doable. That was good. So we did the substitution method. So Dan's idea was to use the substitution method. Solve that first equation for h, and then substitute it into the second equation. It's just kind of a non-traditional substitution from your algebra classes. I think we're good now. Negative 100 plus w times 100 over w to the 4th. Let me add the 100 to the other side. So we'll have 100 over w. Oh, this is boring. Equals 100. So w is 1. That's kind of boring, but that's all right. We'll graph it. We'll see if it's right. It'll be interesting to see if that's right. We still need the h, so the h will be 10 over w squared will be 10. So we want, let's see. Oh, we're not quite
Length.
done. We need length. Good catch. Yep. So length equals 10 over wh. 10 over 1 times 10, so that's also 1. So we want 1 meter by 1 meter by 10 meters. And if you think about it, the top and bottom were way more expensive. So what this is saying is just make like a really tall square. So the sides are giving you most of the volume in the end, and they're the cheapest. So I guess it does make sense. Let's see if we can graph that. I'm gonna pull this maple over to, no, that screen is even, it's got more stuff on it. Okay. Oh no, what was our equation? 20. Oh, I lost it.
Hold on.
Yeah, we need the,
I didn't write it down either.
there it is. No, this one right here. 200 over h. 200 over, we'll call it x.
Plus 20 over w.
So we'll call that y.
Plus 2w or 2xy.
Yeah, xy. Okay. Somebody's dinner's ready. Is that you, Dan?
Yeah, that's fine. Just call my brother, not me. I put a sign on the door.
All right, so I'm going to go 0 to 5, and then y 0 to 20. Uh-oh. Oh, X Maple is very picky. It wants a multiplication sign. There we go. Whoa. Oh, we're still zoomed in. Okay, this is bad. I need to delete this and start over. It was using the zoom factor that we had on the old one. Okay, that's better. So X, which one was the 10? Because it doesn't look like I went far enough. We're not at the minimum yet. I think X was X height? See, I don't think I went out far enough. I think that one should be 10. Right? Yeah.
Yeah, x was height.
Right? So
Yep.
now you can see 1y here, and then 10x. There's our minimum right there. It's a little hard to see on this graph, but the minimum cost is right there. So you don't want a graph way up here that has a small sides or small, like that has a really wide top and bottom. So that minimum though is right there, 10, 1. Wonder if I can, I'm gonna try one more thing here in this maple, see if I can show that. Display, point plot 3D. 10, comma 1, comma, what do we get when we plug in 10, 1? 20 plus 20 plus 2, 222. Oh boy. What are the odds that I have typed in the maple commands correctly? Probably not great. Nope. I got it in the right spot, but I got the y value wrong. 20 over, oh, it's 10. It's 20 plus 20 plus, so 60. There it is. You see that point in the bottom there? You see it now? It's really small. So now I have that point on the bottom there. That's that minimum. That's the minimum point that we just found. And that's going to be the lowest that you can get. And I'm kind of like disoriented here, but that's the smallest cost you can get is right at that minimum point right there when 10 tall and 1 on each side. So back to the point question here. That's our answer. That's our box, 1 meter by 1 meter by 10 meters. We could do the second partials test to prove that it's a minimum. We're not going to take the time to do that right now. It is the only critical point. There are no other critical points. And you can see that if one of the sides goes to 0, the only way to get a volume of 10 is the other side has to blow up. So then the cost becomes infinitely large. So this is the only way to get a minimum. So. All right.
Gotcha.
Christian is falling asleep. I'm hungry for dinner.
My dinner is ready.
Yeah, your dinner is ready. You've been informed your dinner is ready. I'm going to stay on for a couple more minutes if anybody has questions you want to ask, but you are free to go and we'll call it a night. We will plan on meeting again next Wednesday at 4. You're welcome to crash the 2 p.m. sessions next week if you like.
I will do that on Monday.
Yeah, that's fine. And you can come and go. All the recordings are posted on my YouTube channel. For yours, I'll post them on your news page because they're your class. But if you subscribe to my YouTube channel, but if you go on the YouTube channel, you'll see all the discussions are posted. But they're like, it's spammed right now because every class has discussions and they all get posted. And so it's a little bit of a spammy there. But I'll post a quiz tomorrow morning on 15.5, 6, and 7. Next week, we'll go over review questions, answer any more homework questions you have, talk a little bit about 15.8 and 16.1. And then we'll post the exam for Thursday on 15.1 through 7. 15.1 through 7 will be posted a week from tomorrow.
Okay.
Good?
Thank you.
So is your 2 p.m. class? They're a little bit ahead right now, though, right? So if I did join that, let's say that I probably wouldn't know what's going on.
No, Monday I think you'll be all right.
Okay.
I'm gonna try. See, I want you to work really hard right now, so that we can get caught up.
Okay.
You know, that's my goal. So Monday, we'll see. Why don't I tell you for sure? Maybe just if you want to come, maybe just email me. And say, hey, what are you going to be doing on Monday? And then I can let you know, oh, we're going to be going over 16.1 or 16.2, whatever it is, probably 16.2, maybe 16.1, and just, oh, okay, I'll just watch those videos before class then.
Okay.
Yeah. So just email me if you're interested in coming, and I'll let you know what we're going to cover. Maddie had a question about the time. I'm not going to restrict the time. So it's just going to be released and you'll have all day. The quizzes, you should not be taking that long on them. And I don't, there's nothing bad if you do. But they're intended to just be like 2-3 questions, you know, so just like a half hour. And the exams should be like an hour and a half, something like that, hour 45 maybe max if you're, yeah, it should be like an hour and a half. No camera, no, don't record anything. We're not going to be in a Zoom or anything. I'm just going to post it and you work on it. Yeah, sorry, Maddie was commenting the questions. So. And I'm saying Maddie, I don't know if that's who you prefer. I'm just saying what your name is here. So I don't really know anybody. And I feel bad. I wish other people had pictures because then I could, like I know a couple people from previous classes, but most people I don't know. So I don't know who all these people are.
Are you teaching differential equations?
No, that one is in pretty high demand. And so we end up rotating that one. I did my rotation like a couple of years ago, and there's like 5 of us that want to teach it.
Oh,
So yeah, we only have a couple a year. Some semesters we have 2. Kind of
yeah.
like
Every college has it in the morning. There's no afternoon class. Just
oh, really?
yeah.
'Cause I always taught it in the afternoon. I always did like a 2 o'clock. There's no there might not be any evening, like late afternoon. Is that
Yeah,
what
I'm
you
talking
mean?
about late, at 4 o'clock, 5 o'clock.
Yeah, it might be like an enrollment thing for us. We might not have the demand for that. Yeah, it's hard. It's hard as we have faculty who try to figure out the schedule and what things will work. And, you know, it's hard to know. What you don't want is you don't want to set up a class and then you have somebody prep for it and then like 6 students register and the dean's like, sorry, we can't afford that. We have to close that section. And then you're like,
that happens a lot in Wabansi. That's why I'm taking the class here.
sure.
I mean, they have the morning class fills up, but the late night only like 7 or 8 people, and they end up dropping the class.
Yeah, I know in the past, I always made the argument for some of these classes, especially where there just weren't other options, to argue like we need to be available for these students and have a small section for them, especially in the math department. See, some deans will look at, everyone else can go, by the way, like you don't need to hear all this discussion if you don't want to. I will not be offended, but some deans will look at it as a cost thing. Well, I need to have a certain number of students in a section to make up for the cost for that faculty member, which I think is a terrible way to look at it.
Yeah, it's usually like 13 students.
Right. So I need to look at the math department as a whole. Like most of our classes are 95% full. Like we make a ton of money for the college. And so for me, especially when you have students on the engineering track that are working and that's why they need the evening class, that's why I make the argument for like, we need to be here for those students. Like you're naturally just gonna have less and less students the further you go in the math sequence. And there's a reason why they're taking evening classes, you know? So I always made that argument. So that's why we have a Calc 3 at night. That's why Professor Teicher teaches a late evening one or late afternoon one. And so, yeah, I don't know about the DiffyQ, but yeah. Anyway, I gotta go. My wife's waiting for me. Dinner's waiting for me. I got some good Costco pasta tonight.
Thank you so much. Have a nice
Hey,
night.
yep. Thanks, everybody.
Thank you.
Yep. Nice to meet you, Dan. I'll be posting some stuff. Take care, everybody.
All right, sounds good.
Okay.
See ya.
All right. Cheers.